Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 23. Today we're going to be talking about the properties of special triangles, specifically an isosceles triangle. We will have some vocabulary to define, an investigation with the base angles, and then we'll come up with the isosceles triangle conjecture. Then we will try an investigation with the converse to see if it's true. And last, we will end with a review in algebra on writing linear equations. So what was our definition of an isosceles triangle? It's a triangle with at least two congruent sides. So here's a picture, and here are our two congruent sides. Our vocabulary is that we have a vertex angle, and the vertex angle is going to be the angle between the two congruent sides. The other two angles we will call base angles, and the line between the two base angles we will call the base. Then we have the sides that are congruent that we call the legs. Our first investigation will be with the base angles and an isosceles triangle. If you're not working with more than one person, draw at least two different angles for this investigation. Draw one of them acute and one obtuse. If you have a group to work with, then everybody can draw a different sized angle. Draw your angle on patty paper and label it C. This angle will be the vertex angle of your isosceles triangle. In our picture, that was the one at the top. Place a point A on one of the rays of angle C, and then fold your patty paper so that the two rays match up. You could also use your compass to draw a point on the same distance on the other side. Trace point A onto the other ray and label it point B. Are CA and CB congruent? Well, they should be. You just trace them, and you trace them so that they would be congruent. So then draw the last line of a triangle AB. You have now constructed an isosceles triangle. Do you know for sure that it's an isosceles? How do you know? What did you do to make sure that it was an isosceles triangle? Use your protractor to compare the measures of your base angles. What relationship do you notice? Can you fold your paper to confirm your conclusion? And last, do a second or third triangle with different vertex angles. Is the relationship the same for every isosceles triangle? Let's look at a video of how this was done. So here's my triangle, and I had already drawn the triangle, but if I hadn't, I would have marked the point A onto the other ray, connected A and B. Knowing that AC and CB are congruent, then I'm going to measure my base angle, and that one was 54. The other base angle was also 54. Here's another isosceles triangle. I'm going to measure the base angles, 31 and 31. I can fold my paper on top of itself to confirm that both of those angles match. So our conjecture is, in an isosceles triangle, if a triangle is isosceles, then its base angles are congruent. You should have proven that to yourself as you drew triangles, and you could also see that in the video. So if a triangle is isosceles, its base angles are congruent. What does that mean in an equilateral triangle? An equilateral triangle does have at least two congruent sides. It fits the definition for an isosceles triangle. So this conjecture should apply to the equilateral triangle too. Think about how it works. What would you call the base angles here? Well, if you're looking at the right side and the bottom, then you would call the angle at the top and the angle at the left side the base angles, so they would be congruent. If I'm looking at the vertex as the one on the left, then my base angles would be the top and the right one. And so they would be congruent. If I look at a different vertex angle, I could have base angles at the bottom, and they would be congruent. In other words, in an equilateral triangle with three equal sides, you will have three equal angles. Knowing that a triangle is 180 degrees, what would each angle B in any equilateral triangle? I hope you said 60 degrees. That's right. So what about the converse? Remember that a converse reverses the if and then statements. So the isosceles triangle conjecture reversed in the converse would be, if a triangle has two congruent angles, then the triangle is isosceles. But is that true? Let's do an investigation. First, draw a segment and label it AB. Draw an acute angle at point A. This will be our base angle. Could you have used an obtuse angle as your base angle? Remember that base angles are going to be the same measurement in an isosceles triangle. So could you have two obtuse angles in any one triangle? No, you can't. You would get more than 180 degrees. So you have to have an acute angle as your base angle. Copy angle A at point B on the same side of AB. Label the intersection of the two rays point C. Then use your compass to compare the lengths of side AC and BC. These would be the legs of your isosceles triangle, if it was an isosceles triangle. Is it? Do you notice the relationship? Can you use your patty paper to confirm? Let's look at how this appears. Here's AB, and I'm drawing an acute angle at A. I'm going to use my compass to copy that angle at point B. So now I can draw a congruent angle at angle B. Now I'm going to measure sides AC and BC and find that they are the same. You can measure them with your compass or even just a ruler. So the converse of the isosceles triangle conjecture. If a triangle has two congruent angles, then it will be an isosceles triangle. Now on to our algebra review. A linear equation graphs a line. We look at the equation, and the y-coordinate at which the graph crosses the y-axis is called the y-intercept. So here in this picture, we have the linear equation, or the graph of a line, as blue. Where it crosses the y-axis, remember the y-axis is the one that's up and down, that is our y-intercept. We use a B to represent this. The measure of the steepness of the line is called the slope, and we use M to represent the slope. Let's talk a little bit more about the slope. We often say that the slope is rise over run. We could write that even as a fraction with rise on top and run as the denominator. The difference between the y values of 2 points on the line divided by the x values of the 2 points on the line can give us the slope. Because remember, our y is our rise, our up and down, and our x is our run, or our back and forth. So the difference in the y values is going to tell us how far up we have gone or how far down we have gone. And the difference in our x values is going to tell us how far we've gone back and forth. Here, this purple line, let's look at our rise. So between this point, 1, 2, and the point 4, 3, we can look at our y values between 2 and 3. We have a difference of 1. So that's our change in our y, or our rise. How far we've gone across, or our run, is going to be a change in our x values. So an x value of 1 and an x value of 4. The difference between 4 and 1 is 3. So 3 is our change of x, or what we call our run. If we put our rise, our 1, over our run, our 3, we get 1 over 3. That is the slope of this line. So our formula is y2 minus y1 over x2 minus x1. And all that's saying is that we have a point on the line, x1, y1. In this case, it was 1, comma 2. Our x1 was 1, and our y1 was 2. And then we had a second point on the line, our x2, y2. In this case, we used 4, 3. We then plug in those numbers, or our change in our y over our change in our x, and that gives us the slope. So all you have to do is take 2 points on the same line, and they don't even have to be right next to each other. They could be further away, and this formula would still work. Look at these lines and equations. Can you see where the slope is in the equation and where the y-intercept is? So here the equation is y equals 2 plus 3x. The slope is 3, and the y-intercept is 2. This is the blue line right here. So that 3 slope is pretty steep. You can see that that line goes up pretty quickly. It also intersects the y-axis at 2. That would be our y-intercept. Next one is y equals 2x minus 1. Our slope is 2, and our y-intercept is negative 1. That's this red line here. The slope isn't quite as steep, and it intersects the y-axis at negative 1 down here. Our third line, negative 3x plus 4. The slope is negative 3, and the y-intercept is 4. That is the yellow line. You can see that it goes downhill from left to right. Because of that negative slope, it's going to go down. And it intersects the y-axis at 4. The last line is our green line, negative 5 plus 3/2 x equals y. Again, our slope is the 3/2, and our y-intercept is negative 5. That means it doesn't intersect the y-axis until way down here at negative 5. That 3/2 is positive, so it is going up, but not quite as steep as 3 or even 2. The slope-intercept form of a linear equation is y equals mx plus b. Remember that m was our slope and b was our y-intercept. Do you see where the slope of these equations is the coefficient number in front of x? So even going back to look, our slope could be in the first spot or the second spot, but it was always what was the coefficient in front of x. That was where our slope was. And our y-intercept is just added to x on the same side of the equation. So let's do some examples. Line AB has a y-intercept of negative 2 and a slope of 3/4. What is the equation of the line? Well, I'm going to start with my basic equation, which is y equals mx plus b. I'm going to remember that m is my slope, so I'm going to put in 3/4 for m. And b is my y-intercept, which in this case is negative 2. So I'm going to put that in for b. I leave my y and my x in the equation. That's needed. So y equals, m is going to be 3/4 times x, and then plus b, and my b is going to be negative 2. So I'm going to write it as a minus 2. And that's it. That's the equation of the line. Given points C, which is 4, 6, and D, which is negative 2, 3, what is the equation of line CD? Now this one might take a little bit longer. First, we need to find the slope. So remember that our slope is rise over run, and that can also be stated as the change, which we can symbolize as a triangle, which is the Greek letter delta. Change of y over change of x. I like to just write it this way instead of the y2 minus y1, but what I'm going to do is I'm going to subtract. So this is my point 1 and this is my point 2. I'm going to take 2.2 minus 0.1. So in my y's, that would be 3 minus 6. In my x's, that will be negative 2 minus 4. 3 minus 6 is -3. -2 minus 4 is a -6. And then I'm going to reduce this fraction. I notice that I have a negative on the top and the bottom, so that's going to make the whole thing positive. And then 3/6 is the same as 1/2. This is my slope. Now, how do I find my y-intercept? Well, there's a couple ways to do it. I'm going to choose to go ahead and write my equation as much as I can. Y equals 1/2 x plus b. But I still don't know what b is. I do know that my x and my y would be any point on the equation. So I could use the point 4,6, or I could use the point -2,3 as my x and my y. And if I plug in an x and a y to this equation, I'll only have one variable. Algebraically, I can solve an equation that has only one variable. I'm going to go ahead and choose to use those positive numbers, so 4 and 6, for the x and the y. And I'm going to put them right into this equation. So my y is going to be 6, 1/2 times x. X is going to be 4, plus b. Now I have an equation with only one variable, and I can solve this. 1/2 times 4 will be 2. So 6 equals 2 plus b. You can probably already see, even without subtracting. But I'll go ahead and subtract the 2, move it over to this side. 4 is equal to b. So now I just have to plug 4 in right here. So the last thing I do is rewrite this equation with the 4 plugged in for b and the x and the y as part of the equation. Y equals 1/2 x plus 4. And that is my final answer. That's the equation of the line CD. One last example today. Find the equation of the perpendicular bisector of the segment with endpoints 2, 9 and -6, -7. Wow. We not only have to find where it would bisect, but also how it would be perpendicular. Remember the relationship that we talked about in the last review between parallel and perpendicular slopes. So let's find the slope of this line first. I'll call it the segment because it is a segment with these endpoints. So the slope of the segment is going to be rise over run, or my change in y over my change in x. Again, I just take 2 minus 1. So my y in point 2 is -7, minus my y in point 1, which is 9. My x of point 2, which is -6, minus my x of point 1, which is 2. -7 minus 9 is -16. And -6 minus 2 is -8. Again, I have two positives, which makes it, two negatives, which makes it a positive. 16 over 8 is just 2. So my slope of the segment is just 2. Now, I want the slope of the perpendicular line. So how do I change that? Remember that parallel lines would have the same slope, but perpendicular lines are going to have the negative reciprocal. So the reciprocal of 2 is what I can multiply 2 by to get 1. Or we can think about it as flipping a fraction. So our reciprocal would be 1/2. And then I make it negative. That is going to be the slope of the line. So now I have the slope of the line, but where does it need to cross this segment? It needs to cross halfway. I'm going to draw a very general picture of what this segment looks like. It is 2, 9, and -6, -7. Probably out a little further. Okay, so halfway should be somewhere around here. So we're looking at the second quadrant, most likely, if my picture is drawn a little bit to scale. Okay, and how do I find that point? Well, it's going to be halfway between 2 and -6 and halfway between 9 and -7. So we'll call it the midpoint. And the x value is the average of these x values. So I'm going to add them together and divide by 2. That gives me the average between these 2 points. And then my y value will be the average between these 2 points. So 9 minus 7 divided by 2. 2 minus 6 is -4. -4 divided by 2 is going to give me a -2. 9 minus 7 is going to give me 2. 2 divided by 2 will be 1. So my midpoint, or the line that I want to go through, the point where I want my line to go through, will be -2, 1. So now I have the slope and I have a point on the line. Remember from my last example, I'm going to start with y equals mx plus b. And I can plug in the point from my x and my y, and I can plug in the slope. When I do that, I'll just have to solve for b to get the final equation of the line. So this is x and y. This is the point through which I want my line to go. My slope is -1/2. My x is -2, and then plus b. So -1/2 times -2 will give me a positive, and it'll be a +1. So now I can see that b is 0. So last thing I do is I plug in m and b, and I leave my x and my y. So y equals m, which was -1/2, times x plus b, and since it's 0, I'm not even going to write down the +0. This is the equation of the perpendicular bisector of that segment. Thanks for watching. See you next time.